Hello, I'm Dr. Ian McCullough of Johns Hopkins University. This is a short lecture on relational algebra. Our objectives for this lesson are to define relational algebra, understand how to construct their operations and what they mean, and then extract networks from relational data is why we're ultimately doing this. Let's return to the genius problem that we looked at in one of the earlier lessons. If you recall, the genius problem was focused on this graph G, which is displayed here in figure 1.1. And the two questions are find the adjacency matrix A of the graph G, and then find the matrix giving the number of three-step walks for the graph G. We learned how to determine the adjacency matrix in an earlier lesson, and this network is a four-node network, and the elements of the matrix A correspond to the number of one-steps between nodes. So there's one step between node 1 and 4. There are two steps between node 2 and 3. The resulting network is therefore displayed here, where you see that there is the two paths from node 2 to 3, or from 3 to 2. So this is the number of one-step walks. So that's the first step of the genius problem. We've created the adjacency matrix for the graph. The second part is determined by multiplication. So what does a matrix mean in relation to a graph? What it means is how many ways can you get from one node to the next. So it's basically telling you how can you skip in one step from a node to another node. When we multiply the matrix together, what we're saying is how do we make two steps through the network, right? So right now there is one step from node 1 to node 4 here. In two steps, how can I get there? Well, I can go through node 2. I can go 1, 2, right? To get to node 4. That allows me to get there in two steps. Is there any other way that I can get there in two steps? I don't see it. So the element from 1 to 4 should be one way to get there. 1, 2, 4 is what it means. If I look at node 2 to 3, okay, in two steps, I can go from 2 to 3, but then I have to go again. I have to go from 3 back to 2. So am I able to get to 3? Well, perhaps. Let's see. If I go from 2 to 1, and then 1 back to 2, it doesn't let me get it to 3. So in the initial matrix here, where you have an element from 2 to 3 of 2, it doesn't look like there's going to be any way in two steps to get from 2 to 3. Right? I can't just stay placed at a node and not move. So when we conduct this operation of A times A, which you learned how to do, and if you're not familiar with the matrix algebra, I ask that you review again the matrix algebra primer video. But when we multiply A times A, or A squared in this case, you'll notice that that element from 2 to 3 is a 0, because there is not a way to get from 2 to 3 and back in two steps. You can do it in one step, but you can't do it in two steps. You'll also notice that the element from 2 to 2 is now 6, because in two steps I can go 3 and then back, so that's one way. I can go 2 ways, I can go 3 ways, 4 ways, or I can take the high road and then the low road for a 5th way, or I can take the low road, then the high road for a 6th way. So you can take a minute, pause the video if you like, to make sure you understand how many ways you can go from each of these source nodes to each of these target nodes, just so you understand where these numbers are coming from. I know you can multiply the matrix out, and I think that's a good exercise to do. I want you to do that as well, but I also want you to visually look through the network and see how you skip through the network, how many different ways. I'm assuming you've paused the network and you've done the matrix algebra to get the answer that you see here below, and that you've kind of visually inspected the graph to see how you can skip through the network. And now I'm going to ask you to pause this again, and the two things that I want you to do is do the actual matrix algebra of multiplying these two networks together to get the resulting A cubed, which should tell you the number of three-step walks in the network. And once you've done that, I want you to visually inspect the network and go from each element to each element. So how many ways can you get from node 1 to node 2 in 3 steps? So you can't just do this one step and then stop here. You have to be able to do 3 steps, like 1, 2, 3, 1, 2, 3, etc. And see how many ways you can do that. I'm assuming you have paused the video and done this exercise. We'll now go through the answers. So here is the number of 3-step walks in the network. This is the conclusion to the genius problem. And I hope that you have been able to not only get this correct answer, but also visually inspect the network to see the number of ways in which you can do 3-step walks through the graph. If we go to 4-step walks, I think it becomes a little bit difficult to comprehend. But this is important. The takeaways from this are 1, the matrix multiplication, and 2, having a sense of what stepping through a graph means and how a matrix multiplication refers to skipping through the network. We're going to revisit this example that we used in the matrix algebra. So when I have a network here where I have people associated with events, I'm skipping one direction into the network. So it's saying, how are people connected to events? If I look at the transpose, it is now saying, how are these events connected back to the people? When I multiply the 2 matrices together, I'm going from a 1-step walk in the network to a 2-step walk in the network. But because I've transposed this, I'm going from the rows to the elements of the column, and then the transpose is having me go back the other way. So it's saying, how many 2-step paths can I have going through the explosion? Okay, so what does that mean? That means that these agents are now going to be connected if they are both in some way connected to the explosion event. This is what allows me to extract a social network from this data. Once I've extracted the social network, I can then conduct network analysis to identify who's influential. In this particular example of looking at explosive forensics, we tie people's fingerprints to explosive events. We are then able to see by fingerprint who is connected to each other, meaning that they have handled the same explosives. And then that allows us to see that even though each actor was involved in only 2 explosive events, one actor has connections with a group and a second group. And so then he becomes the more influential person to investigate. What are relational algebras? Relational algebra is a formal structure consisting of sets of relationships and the operations to manipulate them. And this is used to trace indirect connections across multi-relational networks like we just did in the example. So multi-relational networks might be not just 2 different types of nodes, but it could be different types of relationships like boss of, colleague of, or kinship networks, parent of. So if we want to go from parent of to grandparent of, we can think about what type of operation would that look like. So for a social structure, there's 2 required elements. One is a dichotomous, so binary ties, 1s and 0s, primitive relations across actors, and we represent those relations by a capital letter. Right? So you can think of boss of, employee of. These are different relations, maybe the same set of actors. The composition operation combines 2 or more of these primitive relations. Right? So we have 2 sets of relations, and we can do this with meaning if it's there's some sort of operation such that T is going to start from some set of source nodes and terminate in a node represented here with a little k, actor k, and the other relation has k being tied to something else. Okay. So a parent of network, if that was T here, right? So you start with the the parent, and it terminates with the child. If there's another relation where this child is now a parent of somebody else, well, now the TU relation will create a grandparent network. So the primitives are combined mathematically to reveal new insights into the structure of the system as a whole. So in that example I just gave you, a parent network can be combined to reveal grandparents. We're going to use some basic mathematical operations we learned in the linear algebra or matrix algebra primer to extract some of these, manipulate some of these primers, or some of these primitives, excuse me. So the first thing we needed to see is when we look at a network, this is a multi-relational network, so we have people and locations. The first question is how many networks are shown? So take a minute and pause the video and study this and see if you can identify what some of the relations are and how many different types of relationships you can infer from this network. I'm assuming you've paused this and taken a minute to study the network, and now let's look at what some of these insights are. What happens if I color the relations? Okay, maybe you want to pause the video again and identify how many networks there are. I'm assuming you've paused the video and you've looked to see how many relations there are. I've colored them. So we have black ties that represent people to locations. We have red ties that indicate marriage relations. We have blue ties that is son of, pink daughter of, green sibling of. Now you could obviously just have child of, so you don't distinguish between the blue and the pink ties. That would be another acceptable choice. But in this you can see that here is one family structure that results in Kat, and here's another family structure that results in Brian, and then Brian and Kat have gotten married and they now live here, whereas their siblings, respective siblings and parents, live at the parents' homes, and that's what this network represents. Why is this important? Well, it's important to understand what are the different relationships that you have so that you can understand what meaning you're going to extract when you start multiplying them, which allows you to skip through the network. Let's look at a slightly different context here. If I show you 3 agents and 1 resource, how many networks are present? Well, from the previous example, you might indicate 2, right? There's a, let's call it an owner of the resource and a user of the resource. So the blue line represents who owns the resource, the red line represents who has used the resource. So there are 2. Owner and used by. Now we'll notice that the owner matrix has dimensions A, number of agents, by R, by resource, whereas the used by network has R by A dimensions. So if we transpose X, we end up getting a resource by agent network. Right? You can see that, remember that taking the transpose reverses the arrow in a network. Used by is also a resource by agent, but what I'd like to illustrate here is the information in Y is not the same as the information in X transpose. Right? You can see that they become very different. If we transpose Y, it becomes agent by resource. Again, however, it's not the same information as in matrix X. Right? So it is important to note that X is not YT just because they have the same dimensions. And we've illustrated all 4 networks in the diagram here, and they're all showing you something very different. It's important to eliminate these networks, however, so you can know how do you skip through the network. How do you connect 2 owners of a resource? How do you connect a couple of users of a resource? How do you connect the owner to the user? Can we think through the relational algebra that is necessary to conduct a mathematical operation using matrix algebra on larger data to be able to understand how we're skipping through the network? So we're going to go through this a little more deliberately. In this case, we're going to go through some very simple examples where we're starting from S, a source node, to T, a target node. And that can be represented by matrix X, where you see we have two nodes, source and target, and we have a connection from the source node to the target node. Well, again, what do I do if I want to reverse the direction of the arrow? Well, I can do that with the transpose, where the rows become columns and the columns become rows. So the transpose basically reverses the direction of the arrow. Let's use this with agents. So going from source to target node, I have agent 1 connected to agent 2. To reverse the connection of that, again, I need to take the transpose of the matrix. So I have X and X transpose. If I add them together, I have now taken a single direction arrow and I've made it an undirected network. So when you take a matrix X and you add its transpose, you've taken a unidirectional network and you've turned it into an undirected network. Here is the operation using matrix notation. I have matrix X transpose. When we add them together, you add each element of the matrix, you can see where this creates a X by X network where it is symmetric, where 1 to 2 is 2 to 1. Let's add an additional relation. As you noticed from earlier in the slides, just because agent is connected to a resource through the information in matrix X, agent by resource, there's a different network of resource by agent, Y, that contains, maybe this is who owns a network resource, and this is who uses a resource. So, what happens if I want to connect agent 1 to agent 2, where I want to say perhaps the owner of a resource knows who's using the resource? It's not always true, but it could be. So how would I go through and mathematically take the information contained here in who owns a resource and the information in who uses a resource and combine it in a way to understand that there's a connection from agent 1 to agent 2? Well, let's look. This information is contained in matrix X. So we have two agents, one resource. Agent 1 is connected to the resource. Agent 2 is not in this information. Matrix Y says how the resources are connected to agents by who's using them. So we see resource 1 is not connected to agent 1, but it is connected to agent 2. Different pieces of information. So when I multiply them together, the multiplication means I'm going from, think about the genius problem. How many steps through this network am I taking? Well, the difference here is the step 1 is going from agents to resources. Step 2 in this case is going from resources back to agents. So X, Y is the multiplication, and that allows me to go 2 steps through the network. When you actually do the math here, you'll see that agent 1 is now connected to agent 2, okay, and nowhere else. If you visually inspect the network using just the primitives here, you can see that there's one skipping of agent 1 to its resource, the resource to agent 2. It's important to both understand the math as well as how you're skipping through the network. The skipping through the network part is what's going to allow you to think abstractly and do the relational algebra. Okay, now let's look at a different situation. In this case, both agents own the resource. So this is like a co-ownership of the network. We still want to connect agent 1 to agent 2 because the relationships are the same. That will also have the byproduct of connecting agent 2 back to agent 1. You'll see this in a minute. So here the information is contained in X. So I want to skip from agent 1 to the resource. I can do that for X. But now how do I skip from the resource backwards across the connection to agent 2? Well, in order to go backwards across the tie, I have to look at X transpose, right? That's going to allow me to skip backwards across the directed links. So this operation of X times X transpose is going to take Agent 1 connected to resource 1, and resource 1 through X transpose now is connected back to agent 1 and 2. So notice that rows become columns, columns become rows. The result is going to be everybody's connected to everybody. So let's look at a more developed example here. So we have 4 agents. The information of ownership is in X. The information of usership is in Y. Okay, so we have these relations. Do 2 owners of a resource know each other? Well, probably, but not necessarily. But if we're going to do that, this is the example we just did, where you're going to say, how do I connect these 2 nodes? Well, I have to say, go along the X direction here, along this link to the resource, and then I need to go backwards along the arrow to connect back to the other individual here. So this becomes an X times X transpose operation. Do 2 users of a network know each other? Or sorry, do 2 users of a resource know each other? Well, in one example, we might say, yes, I used my car this week, so did my 2 kids and my wife. So do we all know each other? Yes, we do. But maybe I used an enterprise rental car this week, and I don't know who else used that rental car. So it's not necessarily the case that 2 users of a resource will know each other. But if we want to conduct this operation, if I want to connect these 2 people together, I have to skip from the agent to the resource. Well, I'm going against the arrow. So that is a Y transpose. And then I can use Y to go along the direction of the arrow. And so this is how I determine the relation or the mathematical operations that I need to conduct to connect these 2 users of a resource. And I can do the similar thing for how do I connect an owner to a user of a resource? Well, I move along X, and then I skip along Y. How do I go backwards from from this agent to this agent? So how does the user know the owner? What would that relationship look like? Pause the video and take a moment to sketch down how you think you would do that mathematical operation. I'm assuming you've paused the video and you've conducted that operation, and we would go backwards across the Y relation, so that's a Y transpose, and then backwards across the X relation, so an X transpose. So to connect this actor to this actor, you would do Y transpose X transpose. Now obviously, when you do this operation, you'd also be connecting this actor to this actor as well, because you're going to go through all of the X relations. Likewise, when you're connecting this actor to the user, you're not just going to connect him here, you're going to connect him to this actor as well. So this is the essence of relational algebra. I'm going to give you one example here where if we start with this relation K, which is defined of a child of, so there's an element Kij equals 1 if and only if person I, that's the row, is a child of person J. So in this case, person 3 is a child of person 4. So if we take the operation KK, right, that matrix would be the child of a child of, or grandchild of. So what I would like you to do is go through the matrix operation KK, pause the video, conduct this matrix operation, and then see if you can sketch out the family tree. I'm assuming you've paused the video, you've conducted the operation, and so the result is this network here, where you see that person 5 is the child of person 4. So let's look at this. Person 5 is a child of person 3. Person 3 is a child of person 4. There is nobody else here involved in that chain. So we can go from person 4 as the parent of person 3 of person 5. We also have person 6, right, is the parent of person 2, but they do not have any relationship to these other actors. So we've done kind of 2 examples in this chart. We focused quite heavily on people by resource, right? So that's oftentimes called the capabilities network. We've also done some relational algebras on people by people networks. So we've seen that it's not just people by knowledge, people by resources, etc. These abstract, where the rows and the columns represent different things. They can actually represent the same set of actors, but you have different relations. Another example would be the transpose of the boss of network would be the employee of network. Okay, so there's different types of relations you can do with relational algebra on a set of just social networks, just actors to actors. We also know that there's different relationships such as friendship, respect, membership, co-membership. These sorts of things can also be manipulated. We can represent people by knowledge, so who knows what, people by resources, capabilities, people by tasks, assignments, and all of these can be combined in different ways. And this chart that you're seeing here is from Kathleen Carley, and this represents different ways in which she says you can conceptualize relationships in an organization of people, knowledge, resources, and tasks. Relational algebra allows you to manipulate these different relationships and extract new networks out of them. So in the examples we did, if we see people being affiliated to resources, can we extract social networks of co-ownership, co-usership, owners knowing users, etc. of the resource? You can do the same thing with knowledge, tasks, or virtually any other type of relation you can construct in the network. This has been a short lecture on relational algebra. Thank you for your time. I'm Dr. Ian McCullough of Johns Hopkins University.